Hello. In this part of video lecture, we are going to discuss about over and under migration, and we'll look at 2D versus 3D seismic data for for migration, or actually we look at the um, what is the effect of 2D and 3D on seismic migration. So there will be two learning outcomes of this video lecture. The first one is to understand the concept of over and under migration. Then the second objective of this lecture will be to establish and design of 2D versus 3D seismic data and how much is accurate to define 2D or 3D and how we can define the line's accuracy. So the over and under migration, if you look at the definition, so when the velocity is higher than the actual velocity of the data is called over migration. And the another way of under migration is to when the velocity is lower than the actual velocity of the data is called under-migrated data. So I'm going to show examples to explain over and under migration. So understanding the under migrated data with a point diffractor. So let's say we have a zero offset section. So we have a point diffractor. So when we record the data, so we have the diffraction hyperbola. Let's assume that the actual migration velocity to migrate this data is 1000 meter per second. So as we are discussing under migration, so we'll use a small velocity than the actual velocity. So once we are using the 8000 meter per second migration velocity, so this will be appearing like this. So actually this is collapsing the diffraction, but because of the velocity is low, that's why it does not collapse all the event of the diffraction. So if we are using a velocity, let's say this was 20% less, this was 10% less than the actual, then it is collapsing a bit more than and then this one. So once we are using 5% lower velocity, so then you can see a very small diffraction hyperbola. But when we use the accurate velocity, let's say we are using the 1000 meter per second, so you can see the diffracted event or the diffracted point has been imaged here. So that is all about the under migration. So this is under migrated, this is under migrated, this is also under migrated, but obviously it has a different capacity. It's 20%, 10%, 5%. So now we look at the over migrated data. So same case, if we have the zero offset section and the actual velocity is 1000 meter per second. So once we migrate the more velocity, let's say we use 5% more velocity. So when we have 1050 meter per second velocity, then you can see this hyperbola become to parabola, converted parabola. So I'm just shifting this time from here to here, so because this just to show this one. Then we use a bit more velocity, let's say 10% higher velocity. So in this case, you can see this parabola is becoming more bigger, and so on. If you're using 20% higher, then the parabola is becoming more and more higher. So in the seismic data, if you see this type of events, like if your point diffractors are converting into parabola, so it means you're using a bit higher velocity. And the same case, if your hyperbola is not collapsing, then it means you are using the lower velocity. So that is all about the over and under migration in case of diffractions or the discontinuities. Also, in some other cases, we have the dipping reflector. So how to understand the dipping reflector concept? So let's say on the left side, we have the zero offset section of the dipping reflector. There are multiple reflectors. So it appears in seismic data like this one. As I given an example in the start of the seismic migration overview. So in that, you can also look when a dipping reflectors appears a bit more toward the right when you are using the lower velocity. An actual reflector is here. So now if you look at the accurate migrated section, which is Actually, the velocity is 1000 meter per second, so it's from A to B. So this one reflector appears here. But if you're using a velocity a bit lower, let's say 5% lower velocity, so the dipping reflector will appear a bit lower than the actual. So if you're using, I think, 10% lower velocity, then it's almost similar or a bit more. If you're using 20% lower velocity, then obviously it is more toward the left, or the angle will be more smaller than this one. So now you can understand how to understand the velocity concept during the migration, which is under or over migration. So, so now let's look at the over migrated data. So it's the same case like we have discussed in the previous slide. So we have the zero offset section, then we have the desired migration. So let's say this is the migrated data with actual velocity, but when we are using velocity 5%, so you see on the back side the reflector is moving toward left. Then when you're using a velocity 10% higher, then actual reflector should be here, but appears to be here and moving toward up a bit. And if you're using 20% higher velocity, then you can see dipping reflector is moving more toward left. So that is actually the difference using the lower velocity and the higher velocity, under or over migrated. So methods for post-track migration. So let's see here. So actually in time migration, why we use this over and under migration. So when actually we have no lateral velocity changes, then we only use the time migration. So in time migration, we have the diffraction migration, such as Kirchhoff migration as well. And we have wave equation finite difference migration, which is also called downward continuation. Or we also have discussed FK migration, which is phase shift, and Gazdav migration, stored migration also including in that. So when we are talking about depth migration, so only we apply the depth migration when there is a lateral velocity changes. So now moving to the 2D versus 3D concept. So let's say we have a block given to us to explore this section. So let's say this is a area which is given to you to acquire your seismic survey. So what you do, you will design line because you have the 2D acquisition geometry. So you will put, let's say, 1, 2, 3, 4, 5 lines in this direction, and let's say you want to have 2 lines crossing this 5 lines. So one line this one, so one line this one. So actually we will get all the data according to this line. So let's say this line has this color. I'm just giving an example of a picture how we can acquire. So once, how about this section, this area which is unexplored. So what you do interpolation. So let's say this is black, this is black. So you will just plot this black here. If this is skin color, then you will plot it like this one. So the results will appears to be like this. So this is not a clear image, obviously, but when you have the 3D data, so let's say this is a subsurface inside, then when you plot your acquisition geometry in all direction, let's say your source and receivers are at each point, and your acquisition vessel or the inland case, you have vibroseis is moving this direction, this, and all direction, and all the receivers are active. So you will have the full data. So based on this acquisition and migration, you will get the clear image of the subsurface. So in this case, I'm using just to show you an example of a picture. So in this, you can see very thin structure or thin things, or like the hair you can image, this one you can image, even the texture of each part of these face you can image, but in this one you could not. So if we compare 2D versus 3D, so 2D you will get these results, but 3D you will have the very clear image. So that was actually just to understand. So I'm giving you one more example, actually it's from literature. So let's say if you have a cube like this one, in that you have a different subsurface structure, like you have two anticline and this is the faulted or the dipping reflector. So when you acquire your data, so you can highlight which reflection is coming from which part. So let's say this anticline, which is green color, is showing with green. The yellow anticline shows with the yellow. The blue is your surface. The red is your dipping reflector. So it appears like this one. So if you see this anticlines appears larger than the actual because it's migrated data. So once we do the 2D migration, so with 2D migration, you can get the flat surface, which is blue color. Then you have the green color anticline. You can get the better anticline, but you're confused with this blue and yellow anticline. So you say this is blue and yellow anticline. And also the dipping reflector, because this one is appearing again here. So like this one, red dipping structure. So that is actually in case of along this pink line. But when you have the 3D data, so in 3D data, what you have actually access of all sides of the data, because you have all the receivers in this direction, and in bin side, in each and every bin. So with that, you will have the red dipping reflector starting from left. Then you have this blue surface, the horizontal surface. Then you have green anticline, which is this one, and then again you have the blue one. So that one is actually to give you a concept about 2D and 3D seismic migration, or 2D 3D seismic data. So that was all about understanding under over migration and also 2D 3D seismic. But that's all. Thank you so much, and hope to see you again.